What's going on, everybody? Mr. Diamond here to work on the impulse or the conservation of momentum example problems. So I've got 1, 2, and then 3 is going to be on the back side of this page. 1 and 2 are pretty straightforward. 3 is going to take a little bit more work. All right, starting with number 1. We have a 1,000 kilogram train car traveling at 24 meters per second before hitting an identical train car at rest. They lock together and continue moving forward, but at what speed? So the first thing that you could do to solve this problem is you could go through and you could work and do the math. So we're going to do that first. That's what I assume most of you would do. But afterwards, we're going to kind of look at another way that we could have considered this problem. So the important thing for this is our conservation of momentum. The momentum at position 1 needs to be equal to the momentum at time 2. So before they travel, or before they hit, and then after they hit, the momentum needs to be the same. So that means the mass 1 and the velocity 1 is equal to the mass 2 and velocity 2. And I mentioned this in the other video. This is a lot like the example problem. We did a couple of them like this. The next one's going to be a little bit more different. But this one's kind of similar to what we'd already been doing. And in this case, we're trying to solve for V2. So I'm going to go ahead and do M1 V1 over M2 equals V2. So we're just going to go ahead and take our mass is 1,000. We're going to multiply that by 24. And then since they're combined together, our mass is going to be 2,000. And at this point, you may notice that the math is actually really easy here. And this is what I was going to get at by the second way you could approach this problem. So the second way you could approach it is that momentum is a 1-to-1 ratio or relationship of mass and velocity. They're directly proportional to each other. So in this case, our mass has increased by a factor of 2. So in order to maintain the same momentum, we would expect that our velocity would decrease by a factor of 1/2. It should go down or be cut in half because this mass was doubled. And if we look 1,000 divided by 2,000, well, that's just 1 over 2, which is 1/2 of 24, which means our V2 is 12 meters a second. So you actually could have solved this thinking about the kind of conceptual side of it as opposed to just the actual velocity side, the mathematical side. Okay, the next one's going to be a little bit trickier. I'm going to go ahead and scoot down my camera so we got a little more space there. Sorry about that, everybody. Calculate the recoil of a rifle that is a 5.0 kilogram rifle firing a 0.020 kilogram bullet at 620 meters per second. Assume the rifle was fired at rest. So the first thing that I'm going to put in here is I'm actually going to put in that bullet because that bullet is inside of the gun at the beginning. So what we're going to have at stage 1 is a combined mass of the bullet and of the rifle, and we know that it's fired at rest. We then know the bullet's going to get shot forward. If you ever shot a gun, you know which direction it's going to recoil, but if not, if you just think about it, our momentum needs to be the same as it was at the beginning. And at the beginning, if we check, our mass at position 1, or mass of both of these things together, is going to be 5.020, but our velocity is 0 meters per second, which means our total momentum at position 1 is 0. There is no momentum at position number 1. So we need our momentums from these two pieces to cancel each other out, which means the rifle must go the opposite direction. It must go back. And this is what they talk about if they talk about kick in a rifle or a gun when you fire it, kind of going back into your elbow, or not your elbow. If it goes back into your elbow, you're probably shooting it wrong, but into your shoulder for most rifles. So whatever these two things must be, they must cancel each other out. I'm going to call this the positive direction. I'm going to call this the negative direction. So first, we have our rifle. Our mass of rifle is equal to 5.0 kilograms. Our mass of our bullet is 0.02 kilograms. Our velocity of bullet is equal to 620 meters a second. And our velocity of the rifle, that's what we're solving for. And we know that P1 is equal to P2, which means 0 is equal to these two things added together. So we have a problem we can set up. We'll have 5.0 times velocity of the rifle plus 0.02 times 620. So I'm going to go ahead and plug that into my calculator. If I rearrange to get VR, or velocity of the rifle, by itself, I'm going to have to subtract this to the other side, and I'm going to divide by the 5. So negative 0.02 times 620 divided by 5. I'm not going to do the negative. I'm just going to know in my head that it's going to be negative 0.02 times 620 divided by 5. We get a kickback of 2.48 meters a second. So even though the bullet's fired at a very, very high speed, because the rifle is so much larger, we get a much, much smaller kickback coming from that rifle. Okay, now we can move on to the tough problem, the one that's actually going to be quite a bit more difficult. This is our spaceship problem. You and a friend are in a spaceship that weighs 23,000 kilograms and is flying at 35.0 meters per second to try to gain speed. Your friend ejects 1,200 kilograms out the back at 5 meters per second, and you're going to try to pick the best of these 3 options between dropping 10,000 kilograms, ejecting 6,000 kilograms at 5.2 meters per second, or ejecting 3,000 kilograms at 3.5 meters per second. What I would recommend at the beginning of this is we want to figure out our P1. We want to know what is our initial, and if I go ahead and do a quick sketch, we're going to do kind of our rocket is flying forward, and then we know that for the first part at least, your friend has ejected something to the back, but we're worried about what is going to happen if we do one of these other options. So our P1 is going to be equal to the mass times the velocity at position 1. And we know both of those. We know that it's 23,000 kilograms, and we know that it's times 35 meters per second. So we can go ahead and plug in 23,000 times 35, not times 3, and we can get our 805,000 kilogram meter seconds. Okay, now what's the reason for doing that? Well, if you think back to last chapter when we had that problem where there was the car moving and kind of going up a hill, and we were trying to look at what the car could do as it was traveling, we figured out that finding the E total, the energy that it had at the very beginning, and then using that to predict along the path was the kind of optimal way of solving that problem. And this is the same approach here. We know that this momentum must be the same throughout. Whatever momentum we have at any given position needs to be equal to this 805,000 kilograms per meter seconds. So what I'm going to do here is I'm then going to set up 3 scenarios. We're going to do each one of these 3 scenarios and see how it will affect our change in our speeds for each of these. So first step is going to be, I want to calculate how much does this change affect it? How much magnitude of momentum does ejecting this 1,200 kilograms cost for our momentum? So it's going backwards. I'm going to call going forwards the positive, going backwards the negative direction. So we're going to say friends. For our friend, they have ejected 1,200 kilograms. It's at 5 meters per second, but it's going backwards, so we're going to call that negative 5 meters per second. And then if we multiply those two together, which you could probably do that in your head, but I'm a little bit frozen right now from being at home, you get negative 6,000 kilograms per meter second. Now, that also, because we started with 23,000 kilograms, this is also going to reduce that amount. So just to keep that in mind, I'm going to write over here 21,800 kilograms. That's how much of the spaceship its mass would have at this point. So now we're going to run through our scenarios. So scenario 1 is that we're also going to eject another 3,000 kilograms at 3.5 meters per second. So what we can then do is we can say that our P1 is equal to P2. Our total momentum at the beginning is equal to our total momentum at the end. So 805,000 is going to be equal to, first we're going to take our friend's information, so we're going to go negative 6,000. We're going to take away 6,000 from that. I'm going to draw this line here to make it a little more clear. Then we're going to have to add our momentum for ejecting this. So it's going to be 6,000 kilograms at, 3,000 at 3.5. So we're going to do 3,000 kilograms at, and it's got to be negative because we're ejecting it backwards. Plus, okay, that 3,000 kilograms, if we take that away from our 21,000 we've already got, we would have 18,800 times a V2. And the reason for that is because this is the momentum from friend, momentum from ejection 1, and then this would be the ship, the leftover ship. Make sure you account for the weight decreasing each time that you're losing something there. So we're going to go ahead and call 18,800, and if you double check, 18,800 plus 1,200 plus 3,000, that'll get us back to our 23,000 kilograms that we had as our total mass before. If we solve all of this for V2, we will get a big number probably. We'll see. Well, not a big number actually. That 805,000 is probably going to help us. So 805,000, we have to add this 6,000. Then we're going to add 3,000 times 3.5. And then finally, we're going to divide by 18,800. So we will get a new speed in scenario 1, or we'll call this scenario A, and we'll go back and I'm going to relabel these as A so we can keep track of them a little bit easier. So A, B, and C. So velocity 2 of scenario A is going to be our 43.6968, or if we round that, 43.7 meters per second, which is a pretty big improvement. We were traveling at 35. That's a good 8, almost 9 meters per second we've improved. But let's see if situation B does us any better. So same situation, P1 is equal to P2. We know our momentum has to stay the same. So we've got 805,000 equals, we're still going to keep our negative 6,000, but now we're going to be using a different amount. We're going to be doing a 6,000 kilograms. Did I write this correctly? Let me check back in the original problem, because I feel like I might have written this down incorrectly. Nope, I did. 6,000 kilograms at 5.2, but that's got to be negative. Plus, and then we're going to do same thing as last time. This time it's going to be 6,000 plus this 1,000, so it's an extra 3,000 down that we're dropping. So it's going to be 15,800 times V2. Now, the reason I was kind of confused about this, and I double-checked to make sure that my answer was correct, I think what I meant to have written down was I meant to have these two swapped with each other. I meant to have it be a higher speed, lower mass, higher mass, lower speed. Because you know, or at least if you've been paying attention, if this chapter makes enough sense to you at this point, you should be able to immediately discount option A if it's written that way. I thought I had written it a different way than I did, and it looks like I was incorrect. So we actually just know for a fact that A is not going to be an option because of the fact that it's got a lower speed and a lower mass than option B. But to prove that to ourselves, just in case you were blindly chugging in or plugging and chugging in these equations, our velocity for 2B in this situation, if we plug it in, we got 805,000 plus 6,000 plus, now we're going to do 6,000 times 5.2. Let me make sure it is 5.2. That is what I have. So we'll get this number, and then we're going to divide that by 15,800. We get a significantly higher speed, or depends, I guess, on what you consider significant. 53.303797, which is 53.3 meters per second. Okay, now for option C, which is really the only other one, again, if you would have noticed that you would have to check between B and C. Our major change here, we still have P1, we still have P2. I'm going to go ahead and get rid of that. We've got 805,000. We've got negative 6,000, just like last time. But now we don't have this middle piece, because what we're doing here is we're just dropping 10,000. We're doing, this is the same kind of situation as when we were like scooping the child out of the cart, or if you're increasing the mass, like what we did with the train example on this last page. So now what we're going to do is we're going to say, okay, we dropped a total of 1,200 kilograms from our friend. Our friend ejected that. That left us with 21,800 kilograms left. We're just going to drop 10,000 of them because they're going to be going in a kind of perpendicular direction. If we're just releasing them from the ship or unstrapping them from the ship, they're not being propelled backwards. Their momentum is not going to be adding or subtracting from whatever we're doing. We're just going to lower the amount. So our 21,800 is now instead going to be 11,800 kilograms, and then we're going to multiply that by V2C, whatever our option of velocity 2 for C is. So I'm going to go ahead and plug all that in. Our velocity to C is equal to 805,000 plus 6,000 divided by 11,800. And we get that this is actually the optimal way to improve it. We get 68.72881356, 68.7 meters per second. So it turns out that our best case scenario is this: if we have the option, if we can either try to throw cargo out the back, we can either check something heavy at a fast speed, light at a low speed, or just take a huge chunk and not try to add to our momentum by throwing backwards. In this specific situation, it is best to just drop the 10,000 kilograms, and that will increase our speed the most. In fact, that will almost double our speed, which makes sense because we're reducing our mass by about a half at that point. All right, so that was example 3. Like I said, a little bit trickier. I really wish I had more time to come up with problems like this. You can kind of tell that the first two are more easily modified versions from other sources, but this one is a Mr. Diamond original. And like I've kind of mentioned, I just really wish I had more time to come up with problems like this. I feel like they're a lot more interesting and have a lot more going on with them, but such is the life we lead, living in Rona times and not having as much time to work on stuff as we'd like. But in the meantime, this has been Mr. Diamond. Sorry to ramble there at the end. Hope you have a great rest of your day. If you have any questions, shoot me an email. Otherwise, I hope to see or hear from you soon. See you, everybody.